Now that we understand the basics of chemical reactions, let's take a second to look in a little more detail at a specific type of chemical reaction. This is what's referred to as an oxidation-reduction reaction, sometimes referred to as redox reactions for short. Oxidation reduction, or redox reactions, are extremely common. In fact, right now, you have redox reactions happening both around you as well as inside of you. There are many different examples of everyday processes that involve redox reactions. For example, combustion, or the process of burning something in the presence of oxygen. When you burn something in the presence of oxygen, you're actually doing a redox reaction, whether it's a log in your fireplace or the gasoline in your car. The human body also burns things for fuel. Specifically, it burns food. When you eat, your metabolism is a series of complex redox reactions that allows your body to turn food into fuel. Also, any process that revolves around weathering or rusting. Those type of reactions also involve redox reactions. In fact, originally the term oxidation reduction came from the idea that most of these reactions revolve around oxygen. So whether you're burning something, whether you're eating food and you need to breathe to survive, or whether something sits outside in the environment rusting, all of those reactions really rely on the presence of oxygen. We know now that there's many oxidation reduction reactions that actually don't involve oxygen, but in a few minutes you'll see why it's an important part of understanding these common reactions. Redox reactions, at their core, are really just a chemical reaction where the atoms that are involved either gain or lose access to electrons. Let's look in more detail about what that really means. Sometimes when an atom gains or loses access to electrons, or those electrons are transferred between atoms, it's pretty easy to recognize. And that's because sometimes the gaining, losing, and transferring of electrons gives us things like ions. Ions always have charges, and those charges help us to know where the electron was transferred to. For instance, we've seen many times that sodium, which in its elemental state is a solid metal, reacts very easily to form the sodium ion. The sodium ion has a +1 charge because solid sodium has to lose one electron to form the sodium ion. Because sodium lost access to an electron in this reaction, we say that this is an oxidation reaction, or in other words, that the sodium was oxidized. The sodium was oxidized because it lost electrons, but where did that electron go? Well, this must be part of a larger reaction, and in fact, this is very common. When sodium loses an electron, it has to be transferred to another element or another ion. In this example, let's transfer that electron to copper. Copper, which forms a 1+ ion, can attract that electron that the sodium loses. When the electron is transferred to the copper, the end result, or the product, is just solid copper. So copper started with a +1 charge, and it gained one electron in order to become neutral, or to have a 0 charge. We would say that this copper was reduced, or a reduction reaction took place. So the atom that lost the electron, sodium, was oxidized, and the atom that gained the electron, copper, was reduced. This is why oxidation-reduction reactions always have both processes taking place. When an atom loses an electron through oxidation, the electron has to go somewhere. Now we'll see that sometimes it's very easy to recognize oxidation-reduction reactions, and sometimes it takes a little bit more work. But as for understanding that atoms that lose electrons are oxidized while those that gain electrons are reduced, there's actually a really simple trick you can use to help remember this. That trick involves our new mascot. Everyone, meet Leo, Leo the Lion. Leo the Lion has been a mascot for chemistry classes for decades, and that's because he's part of a very simple mnemonic device that can help you remember the important rule of oxidation-reduction reactions. You may have learned at some point in your life that lions can make lots of noises, but the one that's important in this class is that Leo the Lion can make a noise that goes grrr. Why is this important? Well, it seems silly, but it's part of a mnemonic device that helps us remember when you lose electrons from an atom, that atom is oxidized. But when an atom gains electrons, it's reduced. Hence the phrase, Leo the Lion says grr. It's a trick and it's a silly one, but it's definitely going to help you remember that any atom that loses electrons is oxidized. While it's sometimes very easy to recognize when atoms gain and lose electrons, sometimes it's not quite as obvious. And that occurs especially when we deal with covalent compounds, or compounds that have covalent rather than ionic bonds. Because these compounds don't have charges, it's a little more difficult to tell how electron transfer happens. For instance, let's look at the reaction of solid sulfur with oxygen gas. When solid sulfur reacts with oxygen gas, they form a product called sulfur dioxide, or SO2. This reaction usually needs pretty high heat to take place, but it's an important one, because anytime this reaction does happen, it forms the product sulfur dioxide, which is actually a precursor to sulfuric acid. As a result, this can have interesting environmental consequences. For instance, when people burn unclean fossil fuel sources, things like really dirty diesel fuel, that fuel contains sulfur, and when it's burned in the presence of oxygen, for instance while driving a truck, that truck will actually release sulfur dioxide in its exhaust. The sulfur dioxide can go on to react with water in the air to form sulfuric acid, which is one of the ways we get acid rain. But let's look at this reaction to figure out why can we be so confident that this is an oxidation-reduction reaction, even though there's no charges. Well, with the lack of charges in most covalent compounds, we need to use a different trick to figure out whether electrons were gained or lost. That trick is to use something called oxidation states. Oxidation states are simply numbers that help us easily identify oxidation-reduction reactions. So be careful, because while oxidation states might remind you of physical states, at least in terminology, oxidation states really just refer to numbers. Numbers that help us indicate whether an atom is able to gain or lose electrons. Let's look at how oxidation states work. There are three basic rules for determining oxidation states, and if you can remember these rules, you'll never wonder whether a compound gained or lost electrons again. The first rule, and usually everyone's favorite because it's so simple, is that any atom in its elemental state will have an oxidation state of 0. Or in other words, any atom which is just an element or just a collection of atoms of the same element is simply going to have an oxidation state of 0. For instance, if I have solid gold, gold has the chemical formula Au, well, gold has an oxidation state of 0. Unlike with charges, there's no special way to write this in, but by convention, a lot of people just draw the number so that they can remember it and write it, for instance, above the element. So gold has an oxidation state of 0. This rule applies to any sample that's made of only one type of element. So for instance, the oxygen in the air around us is oxygen gas. It contains 2 oxygen atoms, but because it's just one element, this also has an oxidation state of 0. Think of that as a charge of 0. The second rule in determining oxidation states applies to what happens if you have a compound, more than one element joined together. In most compounds, the atoms will tend to have the same oxidation state as what their ionic charge would have been. For instance, in a compound like sodium chloride, even though we don't see the charges explicitly written on it, as is the case in many compounds, those different elements will just have the same oxidation state as what their ionic charge would be. So chloride would be a -1 and sodium would be a +1. What about other types of compounds, covalent compounds, and so on? Well, let's look at an example of something like carbon monoxide. In carbon monoxide, we have carbon and oxygen joined together. Oxygen, we know, tends to form a -2 ion, but what about carbon? Carbon usually doesn't form an ion, but this brings us to our third rule. All the oxidation states in a compound must sum to the charge on the compound. If it's a neutral compound, that simply means they have to cancel each other out. If it's not a neutral compound, for instance a polyatomic ion, then all the charges or all the oxidation states in the compound have to add up to what the charge is on the polyatomic ion. In this case, we have carbon monoxide. Carbon monoxide contains carbon and oxygen, and we always assign priority to the more electronegative element first. Oxygen is the more electronegative element because we know that it's closer to fluorine on the periodic table. So we assign it the same number as what we would expect its charge to be, -2. The carbon, while we usually don't think of carbon as having a charge, will have an oxidation state. And that oxidation state is determined by the fact that this compound must be neutral. So the oxidation state on the carbon must be a +2. Let's look at another example. How about sulfate? Sulfate is a polyatomic ion that has the chemical formula SO4 2-. It's made up of 1 sulfur and 4 oxygen atoms, and altogether it has a -2 charge. Let's figure out what the oxidation states are on the oxygen and the sulfur in this compound sulfate. The oxygen takes priority because it's more electronegative. This is usually true of the thing that's written second or last in the covalent compound formula. So I'm going to assign an oxidation state to the oxygen on the basis of what its charge would be if it were an ion. Its charge if it were an ion would be a -2. So now I have to figure out what will the charge or the oxidation state on the sulfur be. Overall, these two things have to add up to the charge on the compound. The charge on the compound in this case is not neutral, it's -2. So what oxidation state must sulfur be in order for these 4 oxygens to add up to a -2 charge? Well, if you're comfortable with any degree of algebra, you can think about this as trying to solve for a variable. Something plus my 4 -2 oxygens has to equal -2. The answer is sulfur must have a +6 oxidation state. So in sulfate, each individual oxygen atom has a -2 oxidation state, while the sulfur, and there's only one of them, has a +6 oxidation state. We'll get more practice with this in a minute, but these basic rules allow us to determine whether oxidation reduction reactions happen and which atom is oxidized and which is reduced, whether there's ions present or not. Now let's look at how to use oxidation states on an actual chemical reaction. You can do this with any chemical reaction to arrive at the conclusion of whether oxidation reduction took place, as well as what was oxidized and what was reduced. The first few times you do it, you might find it helpful to have a chart to help you reason this out. The chart can give you helpful information, like what the oxidation state is for each of the reactants, as well as what it is for the products. Then you can compare. So let's have a chart. Again, this is only an option, and it's something that you might want to start using, but you can always stop once you feel more comfortable with these. So let's determine the initial oxidation state for both the element sulfur and the element oxygen. My sulfur on the reactant side is solid sulfur. It's an element, and it's not bonded to any other element to make a compound. So the oxidation state on this sulfur is a 0. If I want to fill out a chart, I'd say the initial oxidation state for sulfur was 0. Now let's look at the oxygen on the reactant side. The oxygen does have 2 oxygen atoms present, but again, it's just one element. It's not bonded to another one to make a compound. For this reason, we say that the oxygen also has a 0 oxidation state. I'll put that into the table. Now, we move to the product to determine the final oxidation states. Again, remembering our 3 rules from the previous slide, we know that we have to figure out what oxidation state is on each sulfur atom and each oxygen atom. In total, I have 2 oxygens and 1 sulfur. Rule number 1, if it's in its elemental state, it's 0. Sulfur dioxide is a compound. It contains more than one element, so rule number 1 doesn't apply. Rule number 2 says atoms will tend to have the same oxidation state as what they would have for a charge, and we give the priority to the more electronegative element. Between sulfur and oxygen, we know that oxygen is further to the upper right of the periodic table or closer to fluorine, so it's more electronegative. Furthermore, we know that oxygen likes to be a -2 ion. So that's what its oxidation state will be. And I'll put that into my table. That -2 oxidation state applies to each oxygen atom. I have 2 oxygen atoms, and overall the compound sulfur dioxide does not have a charge. It's neutral. So to figure out the oxidation state on sulfur, I have to ask myself, what plus 2 times -2 will give me 0? Or in other words, what minus 4 will give me 0? The answer, easily enough, is +4. So in this way I conclude that the final oxidation state for sulfur is a +4. That's all I need the chemical reaction for, because now I can easily conclude whether each individual element was oxidized or reduced. For instance, let's look at the sulfur. The sulfur started as a 0 and it ended as a +4. Remember, electrons are negatively charged. So for an element to start at 0 and become more positive, 4 more positive charges, were the electrons lost or were the electrons gained in this process? What do you think? Well, for the sulfur to start at 0 and move to a +4, the electrons must have been lost or given up. In other words, sulfur lost access to electrons in this process. Leo the Lion reminds us that when something loses electrons, it's oxidized. So we'd say that sulfur was oxidized during this chemical reaction. We know the reverse has to be true for the other element, but let's check just to be sure. My oxygen started at a 0 oxidation state and ended at -2. In this process, it must have gained 2 electrons. Remember, electrons are negatively charged, so gaining 2 of them will give you 2 negative charges. So in this process, electrons were gained. Even though it looks like there's some inequality here, remember, there were 2 oxygen atoms. Each one gained 2 electrons. So while the sulfur lost 4 electrons, the oxygen, each one, gained 2. The result is we conclude that oxygen was reduced in this process. And it kind of makes sense to say that something was reduced if it started at 0 and ended reduced to -2. One final thing about this and all oxidation reduction reactions before we do another practice. It may seem a little silly to put this much thought into the idea that electrons are simply being transferred around between atoms. But here's why it matters. Many chemical reactions are driven by the fact that certain atoms or certain compounds are able to steal electrons from other compounds. In fact, this is what drives redox reactions. In redox reactions, one element or one compound is always gaining electrons from the other one. This is what ends up causing decay in many processes. For instance, in rusting iron, especially iron on something like a bridge or your car, the oxygen from the atmosphere is stealing electrons from that particular iron. As it does that, it ends up becoming a problem because when something loses electrons, chemical bonds are broken and chemical formulas tend to change. This is why we worry about things that are oxidized, because they're usually not as strong as they were initially. That brings me to my final point about oxidation reduction reactions. A lot of times we're worried both about what happens to the elements involved as well as what they can actually do on their own. For this reason, you might wonder why oxygen has its name tied up with oxidation reduction reactions. Well, you'll notice in this reaction, as in many different oxidation reduction reactions, oxygen gained electrons. This basically means that the oxygen stole electrons from another element. It's a little thief in the molecular world. So by gaining electrons or becoming reduced, we say that oxygen, in this case, is an oxidizing agent. That means it acts as an agent to allow another element to become oxidized. It's easy to remember what the oxidizing agent is, because the oxidizing agent, it itself, has to be reduced. You're guaranteed that if you're looking at an element or a molecule that's reduced, you're looking at the oxidizing agent in the reaction. The same can be true about sulfur, just using the opposite term. Whatever lost electrons was a reducing agent because it helped another element to become reduced. So in this case, the reducing agent was solid sulfur. The oxidizing agent was oxygen gas. And now you know why we get the term oxidizing for these reactions. Let's look at another example. This is the reaction of solid iron with an ionic compound, copper 2 bromide. When this reaction happens, the products are solid copper and iron 2 bromide. Take a second to determine which element was oxidized in this reaction and which element was reduced. If you'd like, you can still use a table to help you figure it out. Pause the video and start it when you're ready to keep going. Our first step in determining what's oxidized and what's reduced is to assign oxidation states to each individual element. In my reactant side, I have iron. The iron is not bonded to anything else, so its oxidation state will be 0. I have the compound copper bromide. It won't have an oxidation state of 0 because it's a compound, and I'm going to assign it so that I give priority to the most electronegative element. Bromide is the more electronegative species here, so I'll assign it what its normal charge would be, a -1 because it's in group 7. I know that there are 2 bromides present, and overall this entire compound is neutral. So what plus 2 -1s will give me 0? The answer is +2. So copper's initial oxidation state is +2, the same as what its ionic charge would be, and bromide's is -1, also the same as its ionic charge. As I move to the product side to determine the final oxidation states, I apply the same thinking. On the product side, copper's not bonded to anything, so its oxidation state is 0. On the product side, bromide is still a -1, and the iron that it's now bonded to must be a +2, because overall I know that final product, iron bromide, must be neutral. So my iron ends with a +2 oxidation state, my copper has a 0 oxidation state, and my bromide is unchanged. If you didn't already, stop the video and decide which element was oxidized and which element was reduced. In this case, my iron went from a 0 to a +2 charge. Remembering that electrons are negative, I can conclude that it must have lost electrons. The copper, on the other hand, started as a +2 oxidation state and was reduced down to a 0. So electrons were gained. And as I just said, when we gain electrons, an element is reduced. When we lose electrons, an element is oxidized. What happened to the bromine? Well, the bromine didn't do anything. The technical term for this is to say that it was just a spectator, just like when we use the term in sports. It means it was something, a species, an ion, or an element that was present that wasn't really that involved in the reaction. Finally, if you didn't already, decide what the oxidizing agent in this reaction is and what the reducing agent in this reaction is. Write their chemical formulas. Pause the video if you need to. The oxidizing agent in any chemical reaction is the thing that's reduced. The thing that was reduced here was copper, but it's important to be careful because it wasn't copper metal that was reduced. It was copper in the form of copper bromide. In other words, whatever form copper took on the reactant side. Because of this, I can say that the copper bromide was my oxidizing agent. My reducing agent is always the thing that was oxidized. Again, it sounds confusing, but just remember, it's always the opposite. So my reducing agent is the thing that was oxidized, which in this case was solid iron. Oxidation-reduction reactions take place all around you all the time. Being able to recognize them goes a long way to helping us understand a lot of reactions both around us and in the human body.